n factorial goes to infinity, grows to infinity very, very fast, right? Exponentially fast. So usually we have this Stirling formula. So n factorial is asymptotically equivalent to n over e, quantity to the power of e, square root of 2 pi n. So meaning that limit as n approaches infinity of n factorial over n over e, quantity to the power of n, square root of 2 pi n, is approaching 1. Right? So they grow. So n factorial grows to infinity at the speed of this speed, right? So n to the power of n over e, quantity to the power of n, square root of 2 pi n. So this is a more precise estimation of n factorial. Here we have the limit, but there we don't even take the limit. Straight up equal sign. The only difference is that instead of having this part, we're going to multiply this part by e to the power of theta n over 12n. So this theta n is a constant that's dependent on n. Right? The whole constant is in between 0 and 1. And we don't know that where that constant is. But that's the approximate estimation of n factorial, more precise than the Stirling formula. So first we're going to prove this lemma. Right, so first of all, log of 1 plus x over 1 minus x is equal to log of 1 plus x minus log of 1 minus x. Then we use Taylor expansion, infinite power series, right? So we're going to require, so of course we require x is in between 0 and 1. Then we have this inequality, which we're going to prove. So that log is equal to x minus half of x squared plus third of x cubed minus fourth x to the power 4 plus x to the power 5 over 5 infinity. Then minus log of 1 minus x, that is equal to negative x. Right? We have minus negative x squared over 2. Right? Plus negative x to the power of cube, but still negative. Negative x cubed over 3. Right, so then every term is negative. X to the power 4 minus x to the power 5 over 5. Infinity. Right? We're going to use this part minus that part. So in which case, expand everything out, right? For these terms, right? For the odd, even power terms. Here we have positive ones. But there we have negative ones, so that they can just cancel out. But here I have positive terms which are all odd powers, right? Positive, I got twice of them, right? But then I still have to multiply by half, right? So in other words, half of log of 1 plus x over 1 minus x is equal to exactly the sum of all the terms of odd power, x plus x cubed over 3 plus x to the 5th over 5, all the way to infinity. All right, so that is if we can just loosen the inequality a little bit, that is no larger than we're going to replace every constant with 1 over 3. And so the whole thing becomes bigger. Yes. So I'm going to copy down this x. I'm going to replace every constant with 1/3. 1/3. Right, factor out of x to the power 3 plus x to the power 5 infinity. So that is equal to x plus 1/3. Right? The formula of infinite geometric sequence, geometric series. Common ratio x to the power of 2, 1 minus x to the power of 2. First term, x cubed. Right? Then I'm going to show this inequality, right? So subtract x from that, right? So subtract x from here. So which means really half of log of 1 plus x over 1 minus x is really no larger than subtracted x, no larger than really x cubed over 3 times 1 minus x squared. Right. So at the same time, is it bigger than 0? Or if we subtract x, right, is this part bigger than 0? Yes, of course, because x is between 0 and 1, right, really, obviously. So then I'm going to replace x with 1 over 2n plus 1 and see what we get. So which means this time I have 0 is no larger than half of log of, let's see, 1 plus 1 over 2n plus 1. 1 minus 1 over 2n plus 1. Minus 1 over 2n plus 1 is less than 1 over 2n plus 1 cubed over 3 times 1 minus 1 over 2n plus 1 squared. Right? So this part, half of log of, right, common denominator, right, 2n plus 2, 2n plus 2. I think eventually we can have 2n plus 2 on the top, and 2n plus 1 will just cancel with the bottom. So I think it's 2n plus 1, 2n, and then we can simplify further, and minus 1 over 2n plus 1 less than this part. So eventually we have 0. This time I can multiply everything by 2n plus 1, right? Cancel out with this one. So 0 is half of 1 over 2 times 2n, no. 2n plus 1 over 2 log of n plus 1 over n minus 1 less than 2n multiplied by this part. All right, what is that? All right, so let's work out the right-hand side. So this time right-hand side, that is equal to 1 over 2n plus 1 cubed. Bottom. 2n plus 1 square. Out here I have 3. In here I have 4n squared plus 4n plus 1 minus 1, cancel that. So I have 4n squared plus 4n. Right? And multiply everything by this part, by 2n plus 1 squared, 2n plus 1 squared. So that way still have 1 over 2n plus 1, and this part is gone. 3 times 4n squared plus n. Right? So that way plus 4n. Yes. So that is equal to, take out, factor out, for example, 4n out here, right? It becomes 12n. 2n plus 1, yes. So that is 12n. So inside here I have n plus 1. 2n plus 1. Right? That's the right-hand side. But remember, I multiply everything by 2n plus 1. Right? So still gonna have to multiply by 2n. So this part will be gone. So in the end, I have 0 is less than n plus half. Log 1 plus 1 over n minus 1 is less than 1 over 12n times n plus 1. Like I said, this part will be cancelled out. So plus 1 on each side, right? Cancel out this negative 1. So 1 is less than log of, put this constant on the top of the, it becomes power, right, inside. So 1 plus 1 over n to the power of n plus half is less than this part plus 1. 1 over 12n, n plus 1, plus 1. Right? So this time we take e on both sides, right? E raised to the power of everything. So e raised to the power of 1, right? The inequality still remains less than e to the this part, that is this part inside. 1 plus 1 over n to the power of n plus half. It's less than e to the power of 1 over 12n, n plus 1, plus 1. And now we've reached this inequality. So let me just rewrite this Stirling formula. So I still have n factorial. Right? I'm going to split up this part, n to the power of n, and I have 1 over e to the power of n. I can put e to the power of n on the top. Right? Flip this. Square root of n, square root of, assign the square root onto n, that means n to the power of half, right? Plus half. So still have square root of 2 pi. So that means the whole thing is approaching 1 as n approaches infinity. Which means if I just multiply this square root of 2 pi, right, then the whole thing is approaching square root of 2 pi. Right, as n approaches infinity. So that motivates me to come up with this sequence. That is n factorial e to the power of n n to the power of n plus half. Then I can work out the ratio between an and an plus 1 to determine if the sequence is increasing or decreasing. Right? That is equal to n factorial e to the power of n to the power of n plus half multiplied by its reciprocal. Right? That's n plus 1 factorial e to the power of n plus 1. And on top I have n plus 1 to the power of n plus 1 plus half. So which means e to the power of n, e to the power of n plus 1. So this will be gone. I just have e. Okay. And take a look at n plus 1 factorial, n factorial. So this will be gone. I still have n plus 1. Okay. Take a look at these powers. Okay. So I'm going to assign the power of 1 onto the base first. Right? So n plus 1 itself times n plus 1 to the power of n plus half. Down here I still have n plus 1 times e, still have n to the power of n plus half. That's equal to n plus 1 cancelled out. Right? They have exactly the same power, n plus half. So I can combine the base. So e stays. E stays. And the base will just become 1 plus 1 over n, right? And power is n plus half. Right? So this is what I have. So which means, like I said, if I divide e over, right, it becomes this part. Divide e over, this part will become bigger than 1. 1 plus 1 over n to the power of n plus half. Divide e over, bigger than 1. And smaller than e to the power of, there's no more 1, right? This one will cancel out. And 1 over 12n times n plus 1. So which means that their ratio is bigger than 1, which means which one's bigger? an is bigger. Right? So which means the sequence is really decreasing. And also, at the same time, the sequence is bigger than 0, bounded below. Right? So which means the sequence has a limit. And that limit is, like I said, that limit is, right, I've used this part as my sequence. And I've shown that using this Stirling formula, right, the limit is actually square root of 2 pi. So I've just worked out this. So this part, like I said, this actually represents an over an plus 1. Right? That is this part. Bigger than 0, bigger than 1, less than e to the power of 1 over 12 times n times plus 1. Right, so which means that part is equal to e to the power of 1 over 12. And inside here I have 1 over n times n plus 1. That is equal to 1 over n minus 1 over n plus 1. Right? To split up the fraction, the same thing. Okay, so that means an gonna multiply an plus 1 over and multiply at the same time e to the power of 1 over 12 times e to the power of 1 over 12 times 1 over n negative. Right? So this part will be removed. And less than an plus 1 times e to the power of negative 1 over 12 times n plus 1. Right? So if I set bn equal an times e to the power of negative 1 over 12 times n, so this part will become just bn plus 1. So which means bn is really increasing, right? So bn as a sequence is really increasing. So does bn have a limit? I think so, right? Because an is proven to have a limit. And e to the power of negative 1 over 12 times n, as n approaches infinity, of course, we will tend toward e to the 0, that is 1, right? So the same limit, right? Same limit as an, also square root of 2 pi. So now we have two sequences. An is a sequence decreasingly approaching square root of 2 pi. Bn increasingly approaching the same limit. So which means an has to be bigger than the limit. Bn has to be smaller than the limit. Right? So bn smaller than the limit. Right? An bigger than the limit. Bigger than or equal to, perhaps. So bn equals an times e to the power of negative 1 over 12n. Less than or equal to square root of 2 pi. Less than or equal to an. Right? So it looks like we can apply the intermediate theorem of continuous functions. Right? If we set f of x is equal to, for example, e to the, that equals times e to the power of 0. Right? So we can set e to the power of x. So which means f of negative 1 over 12n is equal to e to the power of negative perhaps I'll use f of x, e to the power of x times an and of course, yeah. So e to the power of negative 1 over 12n times an. So imagine if we fix n, so f of 0 is equal to the right hand side, right? An times e to the power 0. So now we have a constant that's in between the functional values at these 2 points. Means we can apply the intermediate theorem of continuous functions. So there has to exist a constant Kc. Of course, this Kc is dependent on the value of n, right? Because as n changes, of course, the interval will change, right? Kc will probably change. So Kc n, right? That's in between the interval of negative 1 over 12n to 0. Right, so that this value, right, will equal to exactly f of Cn. Right. So let me just rewrite Cn, right, Cn in this interval. So Cn can be rewritten into negative theta n over 12n, where theta n, of course, dependent on the value of n, and this theta n is inside this open interval, 0, 1, right? Because that way this value will again be in between negative 1 over 12 and 0, right? So that's exactly where this interval is. Right? It's the same effect. So that means, like I said, f of theta n is equal to square root of 2 pi, which means f is an times e to the power of not theta n, but Cn is negative theta n over 12n. Right? So negative theta n over 12n. Right? That's the Cn, right? So equal to square root of 2 pi, which means, what is an? An is this part, right? So really, we want to, what do we want to show? We want to show this part. So which means really n factorial e to the n minus theta n over 12n over n to the power of n plus half. That is equal to square root of 2 pi, right? Which means n factorial is equal to multiply this over to the other side, multiply this under. So n to the power of n over e to the power of n. Right? That is combining this part and this part. I still have multiply e to the power of negative. So multiply e to the power of positive theta n over 12n. So cancel this out. Right. Now I still have n to the power of half. That's square root of n, square root of 2 pi n. And multiply e to the power of positive theta n over 12n. Right? So square root of 2 pi n over 2 pi n. Yes, exactly the result.